Hello everyone. So today we are going to discuss about the protection and deprotection of amine. Protection and deprotection of amines. So we have total of 3 type of amine group. We have 1 degree amine, 2 degree amine and 3 degree amine. In 1 degree amine we have 2 hydrogens attached to nitrogen group or nitrogen atom. In 2 degree amine we have 1 hydrogen attached to nitrogen. And in 3 degree amine we have 0 hydrogen attached to nitrogen. 1 degree amine can be represented as RNH2. So 2 hydrogens attached to nitrogen is 1 degree amine. 2 degree amine can be represented as R2NH. So we have 1 hydrogen attached to nitrogen. And in 3 degree amine we have 0 hydrogen attached to nitrogen. So this can be written as R3N. So these are the 3 different type of amine: 1 degree, 2 degree and 3 degree. Now why we need to protect amine? So there are total of 2 reasons why we need to protect amine. Under basic condition, the hydrogen of nitrogen can get deprotonated. This is the first reason why we need to protect amine. And the second reason is the nitrogen lone pair can attack at electrophile. So to avoid this, we also need to protect amine. So basically we are blocking the reaction. Which kind of reaction? This sort of electrophile nucleophile reaction. So here nitrogen is a nucleophile and this is electrophile. So to avoid this kind of reaction, we also need to protect amines. So now let's look how many type of amine protection are there. So to protect amine, we have total of 8 methods. The first one is Bock protection. The second one is alloc protection. Third we have benzyl protection. Fourth we have CBZ protection. Fifth we have a FMOC protection. Sixth we have amide protection. Seventh we have imide protection. And finally 8th one is called bus protection. So to protect amine we have total of 8 methods, and now we are going to see all of them in detail. We will see protection as well as deprotection. Okay, so first we'll start with benzyl protection. Now what is a benzyl group? RCH2PH. So this CH2PH is called benzyl group. So this can be written as RBN, where BN is CH2PH. Now let's talk about protection. Suppose I have this primary amine. To protect this primary amine, I am using benzyl bromide, or I can use benzyl chloride in presence of a weak base, triethylamine. So this triethylamine will abstract the proton of NH2 group, and then this nitrogen lone pair will attack at this benzyl group to eliminate this bromide ion, and we will be able to generate benzyl protected amine group. Now this reaction is done under weak base. Suppose I do the same reaction in presence of a strong base. let's say I have benzyl bromide and sodium hydride. Here I am using a strong base. So first it will generate a monoprotected benzyl group. But the sodium hydride is a strong base, so this proton will also get protonated and the same reaction will happen once again and we will end up getting dibenzyl protected amine group. So this is the protection of primary amine using benzyl protection method. Now suppose I have a 2-degree amine and I want to protect it. So once again I'm going to use benzyl bromide or benzyl chloride. So this time it doesn't matter whether I use a weak base or a strong base. I will get mono substituted benzyl protect only because we have only one hydrogen to remove. So this is the protection of 2-degree amine. Let's say I have a alcohol this time and I want to do benzyl protection. So here also we will use benzyl bromide, and also it doesn't matter whether we use triethylamine or sodium hydride, simply because we have only one hydrogen to remove. So only mono substitution product is possible. So this is about protection of amine using benzyl group. Now what about deprotection? Let's talk about deprotection of benzyl group. So let's say I have one-degree protected benzyl group, or we have 2-degree benzyl protected group. So this both can get deprotonated and we will be able to get corresponding 1-degree amine or 2-degree amine by using hydrogen gas, palladium supported carbon, and we also need a little bit of acidic media. So to deprotect, you need to remember this reagent. Okay, the benzyl group can get deprotonated using this reaction. And also similarly, the oxygen protected benzyl group can also get deprotected using the same reagent. And you will be able to generate your alcohol back. So this is about deprotection. And what is the byproduct of this deprotection? Well, you get, remember we have pH CH2 as a benzyl group. So in this reaction we are simply adding hydrogens across this bond. Okay, and in this reaction the byproduct is pH CH3, which is nothing but a toluene. Okay, so this is all about benzyl protection. Okay, now I want to talk about something interesting. Suppose I have this reaction. Suppose this is my starting material. We have N-protected benzyl group and O-protected benzyl group. So I'm doing two different type of reaction. In first reaction, I'm using H2PDC under acidic media. And then in second reagent, I'm using is palladium hydroxide supported over carbon and a hydrogen gas. Okay, so we have two different cases. So pause the video and try to solve this reaction by yourself. Okay, so this is my starting material. I have N-protected benzyl group and an O-protected benzyl group. In first condition, I am using hydrogen palladium supported carbon acidic media. In second condition, I am using palladium hydroxide supported over carbon and an H2 gas. And particularly this reagent is called Puelman's catalyst. Okay. So in this condition, H2 palladium supported carbon acidic media, both benzyl group is going to deprotect and you will get this product. But Suppose you want to selectively deprotect amine and want to keep your O-benzyl group intact, then you need to use Perlman's catalyst, that is palladium hydroxide supported carbon and hydrogen gas, and you will be able to generate this product. So this is something interesting, okay? You need to know that selectively deprotection of benzylamine can be done using Perlman's catalyst. So this is all about the benzyl protection. Okay, now the second protection method is we have amide. Now what is an amide bond? So this architect is called amide. So suppose I have a primary amine and I am reacting it with acetic anhydride. The structure of acetic anhydride can be written as, okay, so this nitrogen lone pair will attack at this carbonyl, and through conjugation this whole group is going to leave. The byproduct is acetic acid, and simply you have protected your amine into amide. So this is what we call amide protection. This can also be represented as RNHAC. Okay, this group is called acetyl group, AC. And to deprotect amide, you can either deprotect it using acidic medium, or you can also deprotect your amide under basic condition, and you will be able to generate your amine group. Okay, so how the deprotection happens? So this is my amide. So this nitrogen lone pair can form a double bond here. O minus will form. The resonating structure is, so this is a imine bond. Okay, and this imine bond can be easily cleavable under acidic or basic condition. That's why you can deprotect your amide using acid or a base to generate your amine back. So this is about amide protection. Okay, now what is a carbamate? Carbamate. Suppose I have this. So this architect is called carbamate. Okay, and you need to remember this simply because by changing this R group, we can change the protection strategy for amines. For example, suppose this R group is a tertiary butyl group, then this is what we call BOC protection. This group is called BOC. Okay, so this can be written as N-protected BOC. Fine. Suppose this R group is this group, a biphenyl group. So this is called BPOC, and this can be written as NBPOC. Okay. Suppose this time the R group is CH2PH. So this is what we call CBZ protection, and this can be written as NCBZ. So this whole group is representing CBZ. Okay, now suppose that R group this time is this group. So this is what we call the alloc protection. This group represents alloc, and this can be represented as N-alloc. Okay. Now suppose the R group here is fine. So this time this is called the F mock protection, this whole group, and this can be represented as NF mock. So now let's see all of them in detail. Okay, before we begin, I also want you to know, suppose I have this sort of acyl chloride group and I'm reacting it with my primary amine. So this is simple. This nitrogen lone pair will attack at this carbonyl. Through conjugation, this Cl group is going to leave and we have generated a carbamate. Fine. So this is how we can generate carbamate. And the carbamate, in general, all the carbamates can be deprotected using trimethyl iodide. Okay, this can be represented as Me3-iodine in chloroform, and you will be able to get your RNH2 back. Let me write this as R dash. So you will be able to deprotect your carbamate using this trimethyl iodide group in presence of chloroform. Okay, let's talk about Bock protection. So suppose I have this primary amine. To form the Bock protection, I can use Bock anhydride or I can use Bock chloride. And we also need a base. Okay, we also need a base. So how does it happen? So what is the structure of Bock anhydride? So we know the structure of anhydride is like this, and we want to keep the Bock group. So this is my Bock group, this is my Bock group, and this is a anhydride. So that's why it is called Bock anhydride. So this nitrogen lone pair will attack at this carbonyl, and this CO bond will break, and this is how you protect your amine into a Bock protection. What is the structure of Bock chloride? This is the structure of Bock chloride, where nitrogen lone pair will attack at this carbonyl, and through conjugation Cl is going to leave, and you will be eventually able to form this Bock protected amine group. Now how to deprotect Bock protected amine group? To deprotect, you either need a HCl, acidic condition, or you can use trifluoroacetic acid, another acid group. You can also use CAN. What is CAN? CAN is ceric ammonium nitrate. Okay, or you can also use any Lewis acid. Okay, and what is the formula of CAN? So this ceric ammonium nitrate can be represented as NH4 twice samarium nitrate group. So we have NO3 6 times. So using any one of this, you will be able to deprotect your Bock protected amine, and you will be able to get your NH2 group back. So now let's see the mechanism for this deprotection step. So we have this Bock protected amine, and we added acid group. Okay, so this oxygen lone pair will grab this proton, and we have generated this molecule. Now this bond is going to break. This both electron will be taken by oxygen, and you will be able to generate carbamic acid. Now you have converted carbamate into an acid group. Okay, and here this carbon will get positive charge because this both electron are taken by oxygen. So you have generated carbocation here. Furthermore, the hydrogen attached to this carbon will leave by forming a double bond by satisfying the valency of this carbocation and will generate a isobutylene gas. So this will leave out the system in a gas form. Also, this bond will migrate here, okay, and this bond will break. So this is how you also generate. So now you have generated a CO2 gas. So CO2 gas is going to liberate as a gas, and you have generated your amine. So this is the mechanism for deprotection of carbamate amine protected Bock group under acidic medium. Now let's talk about CBZ protection. People also write it as BZ protection. Okay, so this can be represented as CBZ group is nothing but CH2PH. Okay, so suppose I have this primary amine and I am taking PH CH2. Let me take the chloride version of it. Okay, for example, this we have. So this nitrogen lone pair will attack at this carbonyl, Cl will leave, and you will be able to generate RNH carbonyl. This nitrogen is now attached to this carbonyl, OCH2PH. Okay, you also need a little bit of base, so the reaction will be faster when this hydrogen will be abstracted. Another reagent can be used is a benzyl corresponding anhydride group. We can also use PH CH2 O C double bond O O C double bond O O CH2PH. So this is an anhydride version of it. Similar fashion, this nitrogen lone pair attack at this carbonyl, this whole group leaves, and you generate the CBZ protected amine group. So this is about protection. To deprotect your CBZ and generate your RNH2 group back, you can do this in 3 different ways. Okay, you can use hydrogen, palladium supported carbon. You can also use you can also use hydrogen, palladium supported carbon with ammonia, or you can also deprotect your CBZ group using a KOH MUH, basically a strong base condition. So these 3 reagents can be used to deprotect your CBZ protected amine into corresponding amine group. So what is the mechanism? So mechanism is same. We have, let me write in another page. Okay, so we have the CBZ protected amine. Okay, and we are using H2PDC. So basically this is a palladium supported over carbon, and we have adsorbed hydrogen gas over it. So this is what we call H2PDC. Okay, basically these 2 hydrogen add across this CO bond, and this bond is going to break. So this will generate RNH C double bond O OH and CH3PH. This is a toluene. Okay, and this can be further cleaved as carbon dioxide gas and RNH2. Which leave out as a gas. So this is the mechanism for deprotection of CBZ protected amine group. Okay, now let's talk about FMOC. So suppose I want to protect my amine using a FMOC strategy. So I will start with the FMOC chloride. This is what we call FMOC chloride group. Okay, now this in presence of amine. So this nitrogen lone pair will replace chlorine, and you have simply generated a FMOC protected amine. Okay, we have generated carbamate. Okay, and this group is, that's why we are calling it as FMOC. So this can be represented as R, let me write it as R dash. So R dash NH FMOC. Now this is about protection of amine by using FMOC chloride. Suppose I want to deprotect it. I want to remove this FMOC group and I want to generate my RNH2 back. So I have to use amine bases. What are the amine bases? Like triethylamine I can use. Okay, I can use piperidine. So basically you have to use nitrogen containing bases to remove this FMOC group. So you need to remember that to remove FMOC group and to generate your RNH2 back, you need to use amine bases. A base where the nitrogen lone pairs are acting as a base. Okay, so this is about FMOC. So now let's see the mechanism that how this FMOC is getting deprotected using amine base. Okay, so I'm writing my RNH FMOC. Okay. So this is my FMOC protected amine. Now suppose I have an amine base, let's say I have triethylamine. Okay, so if you look closely, hydrogen sitting here is very acidic. So this can grab this proton and it will generate a carbon ion at this position. Okay, so what we have now is I have a carbon ion here, and the reason why this reaction is happening is because we are generating an aromatic ring. Okay, so earlier it was a non-aromatic group. We do not have any conjugation in the middle ring, but the moment I generate a carbon ion here, this whole system is in conjugation and the system becomes aromatic. That's why this reaction moves forward. Okay, so now this lone pair will form a double bond, okay, at this position, and this bond is going to cleave, right? So we have two things. First, we have generated so we have double bond now here. So we have generated an exocyclic system. Okay, and we have also generated this group. Now this oxygen lone pair will form a double bond. This bond is going to cleave. Simply we have eliminated CO2 gas and we have generated RNH2. So this is the mechanism for deprotection of F-MOC. Deprotection of F-MOC back into amine group using an amine base like triethylamine. Okay, now let's talk about alloc group. So suppose I have this primary amine, okay, and I'm reacting it with this group. Okay, this is called alloc chloride. I can also write it as C double bond O, O, C double bond O, O. This will be alloc anhydride. Okay, this is alloc anhydride and this is alloc chloride. So mechanism is similar. This nitrogen lone pair attack at this carbonyl, Cl is going to leave. Attack at this carbonyl, this group is going to leave. And you will generate RNH, C double bond O, O, CH2, CH double bond. Okay, so this is what we write RNH alloc. Okay, now to deprotect this group, we have only one reagent, that is you need to use palladium metal. Okay, this is an organometallic compound. So to get rid of this alloc group, so RNH alloc can be converted into RNH2. You will be able to remove this alloc group using palladium metal in its zero state. So now let's see the mechanism for this step. Okay, so we have this RNH O. Okay, excuse me, sorry. Let me write in a new page. Okay, so suppose I have this alloc protected amine. Fine. So under palladium condition, we are able to generate RNH2. But how? So palladium will come closer to this system and will form a complex with this molecule. Okay, and this bond is going to break. So what we have generated? RNH, C double bond O, O minus, and we have palladium bonded with this whole molecule. Basically it has formed a complex of heptacity 3 because we have 3 carbon system electron rich. Okay, so this is the byproduct of this reaction, a complex between palladium and this allyl group. Okay, now this oxygen lone pair forms a double bond and this bond will break and you will generate RNH2 and a CO2 gas. So this is a deprotection of alloc group in presence of palladium. Okay, now let's talk about the bus protection. So this is my RNH2, my amine. I want to do bus protection. So the reagent I'm going to use is called tertiary butyl SOCl. Now what is this? So S double bond O, Cl and a tertiary butyl group. So mechanism is same. This attacks here through conjugation, Cl is going to leave and you can generate RNH, S double bond O, tertiary butyl. This is what we call RNH bus. Okay, this is what we call the bus protection. And to deprotect this bus group and to get your RNH2 back, you need to use acidic medium. You can use trifluoroacidic acid or you can also use triflic acid. So this is about the bus protection. Now let's talk about the imide protection. Okay. Now what is the imide group? This is what we call imide protection. Okay. This whole group is called imide protection, and this can be represented as RCH2 NH imide group. Okay. Now let's see the mechanism. Let's see how we can protect amine using an imide strategy. So we have this primary amine. The reagent you need to use looks like this. Okay. C double bond O and C double bond O, C double bond O, OET. So this is the reagent you need to use to protect your amine using imide protection. So what is the mechanism? So this nitrogen lone pair will attack at this carbonyl. Okay. Through conjugation, this bond is going to break and will collapse on nitrogen. So the intermediate is like we have carbonyl group. Now this carbonyl is attached to this group. Let me write this as R dash. So we have NH R dash, and here we have carbonyl group N and a carbonyl group and a OET. Okay. So this will also get a proton. Now furthermore, this nitrogen will attack at this carbonyl. Okay. And through conjugation with oxygen, this whole bond is going to break. And we have generated C double bond O. Basically this is getting cyclized through here. N C double bond O. This N carries R1. Okay. So this is the R dash NH imide group. This is what we call imide protection. And byproduct for this reaction is NH2 C double bond O OET. Okay, so we have generated NH2 C double bond O OET. This is the byproduct. So this is about protection of amine group using imide. Now let's talk about the deprotection. Okay, for deprotection of imide, so the imide group we have generated is this one. Now to deprotect it, to do the deprotection of imide, you need to use hydrazine. Okay, so you need to remember that deprotection of imide can be done using hydrazine. So this is the structure of hydrazine. Now what is the mechanism? How we will get this RNH2 back? So this nitrogen lone pair will attack at this carbonyl, and through conjugation with oxygen, this nitrogen carbon bond is going to break, and you will generate C double bond O. Now this is bonded with this nitrogen, NH2 C double bond O NH R1. Okay. Now this hydrogen nitrogen will attack at this carbonyl. Through conjugation, this whole group is going to leave, and now you have generated C double bond O. This is getting cyclized through here. We have N C double bond O. This N is bonded to NH2. So this is the byproduct, and the main product we have taken out as R dash NH2. So this is about deprotection of imide group. So now just a quick revision. that we know the protection methods and deprotection method for amine with detailed mechanism. So there are 8 methods: BOC, alloc, benzyl, CBZ, FMOC, amide, imide, bus. So for BOC protection, you can use BOC anhydride or BOC chloride, and for deprotection you need acidic medium, steric ammonium nitrate, or you can also use the we also use Lewis acid also. So to BOC deprotection we used acidic condition, steric ammonium nitrate, or we can use Lewis acid. For alloc protection we use alloc anhydride or alloc chloride, and to deprotect alloc we used palladium metal. For benzyl protection, once again benzyl chloride or benzyl bromide, and to deprotect benzyl group we use hydrogen palladium supported carbon. For CBZ, the same strategy: protection CBZ chloride or CBZ anhydride, and deprotection H2PDC. For FMOC, we used FMOC chloride, and to deprotect we used amine bases. For amide, we specially used acidic anhydride to protect, and deprotect we did under acidic or basic medium. For imide, we used special reagent, and to deprotect we use hydrazine. For bus also, we use a special reagent like tertiary butyl SC112Cl, and we deprotected using trifluoroacetic acid or triflic acid. So I have discussed in detail about all the protection and deprotection of amines, and in upcoming video we will solve lots of practice problems regarding this all 8 methods. So this is it, and thank you for watching.